Okay, we're now on chapter 9, problem 29, and what we have is a knee that we're trying to exercise, basically, or leg we're trying to exercise. And the way they're doing it is they're attaching a strap to the leg and using a wire to run up and over and come to a 10 kilogram weight, right? So the 10K weight, 10K weight gives you 10 kilograms times 9.8 meters per second squared, right? In force directed downward. Well, this is a cable going over pulleys, so that ends up directing that force right here, right? So the force here is 10 kilograms times 9.8, so that's 980 newtons, right? 980 newtons being exerted right there. The question is, how much force does the muscle have to exert in order to counteract that so that you can get this steady motion? Now, the problem also says, look at the steps and applications of statics, including problem-solving strategies. Well, step one is this a static situation? The answer is, when you're doing this at constant velocity, you are in dynamic equilibrium, but you're in equilibrium, so the sum of the forces and the sum of the torques still adds up to zero. Step two is, let's draw a diagram, which they've done for us, so step two is done. And step three is apply the mathematics or the physics of the sum of the torques is zero and the sum of the forces is zero and all of that. All right. So we're going to start with, we're after this force that the muscle is providing. So we're going to start with that, and we want to add up the torques to zero. And there is another force here, right? There's this force on the knee, and that's the pivot point. So we're going to use the pivot point mathematically as our pivot point for calculating the torques so that we don't have to worry about that force. All right, so what are our torques? All right, so the torque due to the tension, right? The torque due to the tension is a clockwise torque, so that's going to be a minus 980 newtons, and the distance r perpendicular from there to the pivot point is 0.35 meters, right? The torque due to the muscle pulling on the leg, that torque is a counterclockwise torque and therefore positive, so that's going to be the force of the muscle times, in this case, 0.02 meters, right? And this adds up to zero. So if we simply solve for the force exerted by the muscle, we get 980 newtons times 0.35 divided by 0.02. All right, equals 980 times 0.35 divided by 0.02 is 17,150 newtons. 17,150 newtons, right? It's because the weight down here has a much longer lever arm than the muscle. So the muscle needs a lot more force than the weight to create the same torque. This is why they build machines like this for you exercise, because they can use small weights and actually get you a lot of exercise out of it. Right? And the next question is this reasonable? Right? And that's a lot of force. And it is problem setup seems reasonable. Seems reasonable to me. All right, that's it for problem 29.